Hi, in the previous video, we've learned about isoquants and isocosts and how do we put them together in a problem where the company tries to minimize the cost given that they need to produce a certain amount of output, right? We discussed that in this graphically, the line where we've got all the combinations of labor and capital that give rise to the same amount of output are called isoquants. Well, the line representing a given level of cost is called isocost. Only at the point of the tangency, right, we are getting the labor and capital that should be used in a specific combination in order to produce this amount of output at minimum cost. When we use first order condition, we've calculated out that this is the equilibrium condition. If we would put minuses over here and over here, we would find out that this is the slope of the coastline, right? Isocost line, and this is the slope of the isoquant, right? At equilibrium, one is equal to the other. Okay, so look, what would happen now if it turns out that the level of production that we've got is not sufficient and we actually need to increase it? So the new condition would go as Q K L equals to some Q1. And let's assume that Q0 is smaller than Q1. So now we are relaxing our constraint. In other words, we are going to be allowing for bigger output, right? So now we can draw another isoquant that should be parallel exactly. So it should look exactly like this one. However, of course, it should be higher. Okay, so look, what would we do now? Now, what would happen is that if we want to produce this much, we actually need to raise the cost, right? C is going up, and as a result, this line moves parallelly okay, let's assume that those two are perfectly parallel, upward, and we get a new equilibrium point. And look, it might happen that our restriction on how much we should produce is going to be relaxed even more, and we have an order for even bigger output. So here we would see another isoquant like this, and in order to minimize the cost, of course, we need to, that is going to go up, of course, because we are producing more. We need to move the cost line to be tangent. Okay, let's say over here, this point E3. Okay, and look, we could make exercises like this all day. However, if we now connect all these points like this, we would see something that is called expansion path. Okay, and look, in the case, in this particular case, we see that it's actually kind of tilted towards labor, right? And we see that this line simply connects minimum combination for each a combination that guarantees minimum cost for each consecutive level of production, right? And look, in this case, what we can notice is that this line is tilted. And what does it imply? If this line changes slope, it means that the optimal capital to labor ratio is changing. So, for example, a company with expanding production might be deciding to use more and more and more capital, right? So capital to labor ratio can change. However, there is a function that we really like to work with, and it has some amazing properties in terms of the expansion time. The function I'm talking about is, of course, Cobb Douglas production function, right? So what would happen if now we would have production function in the form A, L, alpha, K, beta. We use the general formulation. Look, I'm not assuming constant returns to scale. So, look, we can calculate right away using the equilibrium condition what would be the specific condition if we would use production function, a Cobb Douglas production function that you see over here. So, first we would have marginal product. In order to get this, we need to have first marginal product of labor, which is alpha times A times L to the power alpha minus 1 times K to the power of beta. And we need to calculate marginal product of capital, which is given by beta A L alpha K beta to the power negative 1. Okay, and now look, all I need to do is to substitute those two values into the ratio that we've got over there. So we've got that PL over PK is equal to it goes up. It's alpha A L alpha minus 1 K beta over beta A L alpha K beta to the power minus 1. Okay, and look, let's get rid of everything we don't need. We see that A's are canceling each other out. We see that lambda, L to the power of alpha is canceling itself with alpha, so we've got just L to the power negative 1. And finally, over here, K beta to the power of beta and K beta. So also we've got on the bottom K to the power negative 1. So look, we've got alpha over beta times L goes down, K goes up, K over L. And look, so this would be the equilibrium condition if the production function that we are using is Cobb Douglas production function. And look, out of this, I can easily calculate capital to labor ratio. Right? Which is simply defined as capital divided by L. Right? This is equilibrium value. And I see that it is going to be equal to beta over alpha, right? I divide both sides, multiply both sides by beta, divide them by alpha, times PL over PK. Okay, and look, this result provided us with some very interesting insight. Look, capital to labor ratio is showing us what proportion of capital to labor we are using in a given production technology, right? Now, when we see over here that within our model is absolutely dependent on exogenous parameters only. So what we see is the beta here, the capital intensity, alpha labor intensity, and we've got wage and rent. So all the things that are given. So what does it mean is that proportion of capital to labor used in the optimum at the optimum point. So within the combination that guarantees us minimum cost, it's always going to be the same. So it's going to form a straight line. And this is the amazing result that we are getting from Cobb Douglas production function. In case of Cobb Douglas production function, capital to labor ratio remains constant. And as a result, we will get expansion path that looks like a straight line. And one additional important thing to mention here, look, this result does not depend on economies of scale. So if A plus B is above 1, alpha plus beta is above 1, we will get also straight lines in the expansion as the expansion path. Okay. However, look, it is really good to make a graph that will distinguish between some cases. Okay, first, let's start making a graph that would allow us to show what happens during the production of some good if let's just say alpha plus beta are equal to 1. Okay, so let's start at a situation like this. Okay, we've got some budget constraint, we've got some ISO cost line, and we've got some ISO point. Okay, now look, at the equilibrium point, we have some level of labor L0 and capital K0 that gives us the level of production Q0. Okay, now what we know over here is that this ratio of capital to labor is going to be maintained regardless of how much we produce. So we might say that I am ready to draw an expansion path. Okay. So now what will be happening over this path? Now, if I would take this amount of labor and double it, and if I would take this amount of capital and double it. Okay. I would find a place, I would find an isoquant that doubles the production. And of course, the ratio of prices remains the same. Okay, now, let's do one more thing. Let's just see what would happen now if I would take and triple the labor, okay, and triple the capital. Okay, from these 2 points, okay, you see, this is really hard to draw when you're not a computer. Okay, unfortunately, this must be enough. Okay, so look, what we see over here are constant economies of scale. When we double the level of inputs, we double the output. Now, if we would triple the level of input, both inputs, we would triple, of course, output. Now, we might ask, what would happen here if instead of alpha beta plus beta be equal to 1, it would be equal to 2. Well, then, if I would double the labor and I would double the capital, I should expect to quadruple my output, right? Then, if I would, of course, use 3 units of labor and 3 units of capital, I would get 9 times my original output. Okay, and look, this is another reason why Cobb Douglas production function is so vastly used in economics. Okay, this is it about the expansion path. In the next video, we will talk about homothetic functions. Thank you for your attention. Take care.